On September 5, 1977, humanity quietly launched a machine that would go on to become one of the most extraordinary explorers ever built, Voyager 1. At the time, it was simply part of a planetary science mission designed to study Jupiter and Saturn up close, capturing data and images that Earth-based telescopes could never achieve. No one truly expected it to become anything more than a short-lived scientific probe, operating for a few years before fading into silence. Yet Voyager 1 defied those expectations almost immediately. Built with 1970s-era engineering, limited computing power, and systems designed for a short journey, it began a path that would carry it far beyond its original purpose and eventually beyond the boundary of our entire solar system. As Voyager 1 traveled deeper into space, it delivered some of the most transformative discoveries in planetary science. It revealed Jupiter as a violent, swirling world of storms larger than Earth, showed Io as a volcanic moon constantly reshaping itself, and captured Saturn's rings in breathtaking detail, exposing structures and gaps that were completely unknown before. These observations changed textbooks forever and gave humanity its first close-up understanding of the outer planets as dynamic, active systems rather than distant points of light. After completing its planetary flybys, Voyager did not stop. Instead, it continued outward into the darkness, steadily moving farther from the Sun year after year, becoming the most distant human-made object in existence. Over time, it crossed regions no spacecraft had ever reached before, passing beyond the influence of the gas giants, beyond the Kuiper belt, and eventually approaching the outer boundary of the Sun's protective bubble, known as the heliosphere. This invisible shield, formed by the solar wind, surrounds our solar system and separates it from interstellar space. For decades, scientists debated exactly where this boundary would be crossed and what it would feel like for a spacecraft to pass through it. Then, in 2012, Voyager 1 finally crossed that line. It entered interstellar space, becoming the first human-made object to travel into the vast region between stars. What it found there was not emptiness, but a very different kind of environment. The interstellar medium is extremely thin, yet far from empty. It contains charged particles, cosmic rays traveling near the speed of light, and weak but widespread magnetic fields stretching across enormous distances. It is a region shaped by the life cycles of stars, supernova explosions, stellar winds, and ancient cosmic events that have spread matter across the galaxy for billions of years. Voyager 1 became our first direct sensor in this environment, sending back data from a place no human instrument had ever reached before. As scientists studied its transmissions, they began noticing subtle but important changes. Particle densities shifted in unexpected ways, cosmic ray levels behaved differently than predicted, and plasma wave activity showed patterns that were not fully understood. While most of these observations could be explained through natural astrophysical processes, they challenged existing models and forced researchers to refine their understanding of how interstellar space behaves. Each new dataset from Voyager added another piece to a puzzle that is still far from complete. Even today, scientists continue to analyze its faint signals, looking for clues about the structure and dynamics of the galaxy beyond our solar system. Meanwhile, Voyager itself continues to operate in extreme conditions. Temperatures in interstellar space can fall close to absolute cold, and the spacecraft is constantly exposed to radiation that would destroy most modern electronics. Despite this, it continues to function. Its power comes from radioisotope thermoelectric generators, which slowly decay over time, producing less energy each year. To extend its mission, NASA engineers have gradually shut down non-essential systems, carefully prioritizing which instruments remain active. Every decision is made with precision, because once a system is turned off, it may never be turned back on again. This careful management has allowed Voyager 1 to remain operational far beyond its expected lifetime, continuing to communicate across billions of kilometers of empty space. One of the most important discoveries linked to Voyager's journey is the nature of the heliopause, the boundary where the Sun's influence finally gives way to interstellar space. Rather than being a fixed wall or edge, it behaves more like a flexible, shifting region that expands and contracts depending on solar activity. When the Sun is active, the heliosphere pushes outward. When solar activity weakens, external galactic pressures compress it inward. Voyager's observations revealed this dynamic behavior for the first time, fundamentally changing how scientists understand the structure of our solar system and its interaction with the galaxy beyond it. Alongside its scientific instruments, Voyager 1 carries something far more symbolic: the golden record. This golden phonograph disc was created as a message from Earth to the cosmos, intended for any intelligent civilization that might encounter it in the distant future. It contains a carefully curated collection of sounds, including natural Earth environments like wind, rain, and thunder, along with greetings spoken in dozens of human languages. It also includes music from different cultures and eras, representing the diversity of human expression. More than a scientific payload, it is a cultural artifact, a snapshot of humanity frozen in time and launched into interstellar space. Among Voyager's most fascinating scientific outputs are its plasma wave recordings. These are not sounds in the traditional sense, but electromagnetic vibrations in space that can be converted into audible frequencies. When played back, they create eerie, haunting tones that seem almost otherworldly. These recordings allow scientists to hear the invisible environment of space for the first time. Some of the wave patterns show repetition and structure that researchers continue to study, trying to understand the underlying physical processes that generate them. While these signals are still explained through known physics involving plasma interactions and magnetic fields, they remain one of the most intriguing aspects of Voyager's data because they reveal a hidden layer of activity in interstellar space that cannot be seen directly. Beyond its scientific achievements, Voyager 1 carries a deeper meaning. It represents the peak of human curiosity and the desire to explore beyond known boundaries. It has shown us worlds we had never seen before, from volcanic moons to complex ring systems, and has given us one of the most powerful perspectives ever captured, the famous pale blue dot image, where Earth appears as a tiny speck suspended in a beam of sunlight. That image reshaped how humanity sees itself, highlighting both our smallness in the universe and the uniqueness of our planet as our only home. Today, Voyager continues its silent journey through interstellar space. It is no longer exploring planets or sending back detailed images, but it still communicates faintly across the darkness, carrying the last remaining energy from a spacecraft that has outlived every expectation. Eventually, its power will fade completely, and its signals will stop reaching Earth. But even then, Voyager itself will continue traveling, drifting endlessly through the galaxy for millions, perhaps billions of years. Long after its voice is gone, it will remain as a silent messenger from Earth, carrying with it the story of a small civilization that once looked up at the stars and decided to explore them. In the end, Voyager is not just a spacecraft. It is a symbol of endurance, curiosity, and discovery. It reminds us that exploration does not end when signals fade or missions conclude. It continues as long as something from us moves outward into the unknown, carrying our questions into the vast silence of space, searching for answers that may take lifetimes to understand.